It's more like chess. But you will learn how to do baseball in one of the Max Flow videos I'm going to upload later today. So welcome to lecture 11. This is effectively one of the last lectures of main material for the course. And there's lecture 12 on Monday, but that's going to have a lot of review built in. Like we're going to see a lot of DP, greedy algorithms, graph reductions. So it's not super, you're not going to learn a ton of new stuff. It's more of a review. But today we're going to learn one of the most complicated parts about all of algorithms. So prepare yourselves. Homework 6 was released yesterday. So as I mentioned on Monday, it's due on Tuesday, but it's only 2 problems, and they're mostly meant to be like review for the final. So definitely make sure you do it. There's also solved problems, like I've said a bunch of times, but I just want to emphasize every homework has an associated solved problem, which is like a problem that was basically on the homework, but then we solved it for you and kind of walked through how to write it correctly in the rubric stuff. So make sure you're always looking at the solved problem for that homework so it gives you a better idea of like how to write the solutions and what's expected. And then, like I said, I'm going to release more Max Flow videos to help with the current homework 5 later today, and I'll release a ton of reduction videos probably tomorrow. So that's where we currently are. So any questions so far? Okay, also everyone's moved much closer today. That's interesting. There also might be an optional homework 7, and this is something I thought about at the very beginning of the semester. So the issue with homework 7 is we won't realistically have enough time to grade it. So if there's a homework 7, everybody would have to turn in a single solution for the whole class. So I don't know if everyone's going to want to do that, because then your grade is tied to everyone else's, but it could be a fun experiment, I guess, if people are really interested. It is a possibility, but it seems like a logistical nightmare for you guys. But we can grade a single thing in one day, so it makes it possible for us at least. It's just something to keep in mind. Okay, so up to this part in the course, we've discussed general problem-solving techniques that can show a problem is easy. And by easy, I mean solvable efficiently. So we've seen a bunch of different techniques like break the problem into smaller pieces, that's divide and conquer. We can build a solution from simpler subproblems, that's dynamic programming. We could grow a solution greedily, one choice at a time. Obviously, that's greedy. We can model the problem as some kind of graph problem that we know how to solve. That's graph reductions. We can continuously or iteratively improve a solution till it's optimal. That's Max Flow. That's basically what the Ford-Fulkerson algorithm is doing. It continually finds a better path that improves the flow over time. This is also something called local search, which we'll learn more about on Monday. Then we also know how to solve a problem by solving its opposite. So that's called duality. And that was basically how we solved min-cut through the Max Flow min-cut theorem. So there's this class of problems called dual problems, and if you can solve the dual problem, you also, for free, get a solution to the original, which is called the primal. And the most famous example of this, which generalizes Max Flow, is called linear programming. Again, we'll learn more about that on Monday. But these are all general techniques that can make a problem easy. We can use these techniques to actually solve the problem efficiently. And the idea here is all of these techniques allow us to avoid exhaustive search. So the clearest example of this is probably greedy, because instead of trying all possibilities, you try one out of a ton of possibilities. You're taking a single path in this gigantic graph of options. The other example is DP, where literally we're just removing a huge chunk of the graph and just focusing on critical dependencies. And that's why it runs efficiently. In contrast, general backtracking is not like that. So in general backtracking, like in the n-queens problem, we had to search the entire game tree of possibilities. We weren't able to remove any of those possibilities because if we did, we risk messing up one of the queen's positions. So we have to literally search the entire tree or risk failing the problem. So that's the difference for general backtracking. So general backtracking is a technique in the course you can use to solve problems, but it does not guarantee efficiency. You can solve it, but not fast. And in general, all of this gives you upper bounds, specifically upper bounds on runtimes. So the whole point of these algorithms is not that they're necessarily the optimal, it's not necessarily the best algorithm, but we know an upper bound on how hard that problem is. If you give me an n cubed solution, we know at the most it's as hard as n cubed. There could always be a better algorithm that's maybe n squared, we don't necessarily know, but at the very least we know it's n cubed. So that's an upper bound on the runtime. So on the other hand, what does it mean for a problem to be hard? Typically we're thinking of lower bounds. Can we prove no matter what algorithm you give me for a problem, it's at least this fast? You can't beat that speed. And almost the only example we know of in all of complexity theory is sorting. This is like the only problem we have an actual lower bound for. So we know any algorithm for sorting must run in time at least, so big omega n log n. This is pretty much it. If you ask me for any other problem we've talked about in the entire course what the lower bound is, unless it's a linear time solution, we don't know. This is the only one. So for sorting, we know merge sort is actually optimal because it gets n log n, and n log n is the best we could ever do. If you ever did less than n log n, you've either solved the problem incorrectly or you assume something about the input data. And that's kind of what like radix sort does. So if you've ever heard of radix sort, it's O of n, but only because it's assuming that the input is a very special type of input. So it's not a general sorting procedure. It only works on a subclass of problems. And typically in computer science, lower bounds are the harder part. It's just very hard to argue every single algorithm runs slow, whereas for upper bounds, you just have to give me one algorithm that's fast. So here we just need one alg to prove it's fast or easy to solve. Here we need a statement about all algs are slow. So that's why there's this huge difference in complexity. One requires you to have this for all quantifier, whereas one's just a there exists quantifier. So any questions about that? Yes. Yeah, because you have to show for every single algorithm for the problem, its running time is at least whatever. Whereas for upper bounds, you just have to say, for this specific algorithm, here's a time analysis, like, look at the recursion tree, it's n log n. So it's much easier. In particular, you can never really write down a proof for this because you can't look at every single algorithm ever for a problem. There's infinitely many. So it becomes very complicated. Other questions? So the main theme today is talking about lower bounds, basically. So, hardness. Here's a specific example of a hard problem. In particular, it's a game that you can't win. So imagine you had some random box of switches, and there's a light bulb attached to the box. For a particular choice of switches being off or on, the light will turn on. And a salesman comes up to you and asks you, is there any setting of these switches so that the light will turn on? If you answer correctly, you win $100 billion, just some ridiculous amount of money. But if you're either incorrect or attempt the problem and die before you answer it, then he will take your soul. And you do not want people having your soul, especially if you watch Supernatural. So what do we do in this problem? So here's the issue, right? So inside the box, the salesman tells you there's some kind of circuit. So this circuit is really telling you what's going to be the answer. So if you plugged in, say, 0, 1, 1, 0, 1, you can compute the final answer easily. You just plug in, 0 and 0, the and of that 0, and you can just keep propagating the answers up this tree. You're basically just computing this using dynamic programming or a DFS. So the output, which is this, you can compute it with like a DFS type thing, and then if it's a 1, the light can be turned on. If it's a 0, this specific setting does not turn it on. So your goal is to figure out, is there any way to turn the switches on and off so that the entire thing makes the light bulb turn on? Now the issue here, first of all, is what if this salesman's lying to you? Maybe it's a magical adversary. So let's say you try a bunch of configurations, you try a bunch of settings of 0 and 1, and then you don't try them all. And if you don't try them all, what the adversary will do is make sure the box is empty, there's no circuit at all. And then once you give the answer of no, there's nothing in there, well, he just magically manifests a circuit in there that uses the one configuration you didn't try. And so you'll always lose, guaranteed, unless you try them all. So you need to try all possible 2 to the n configurations of switches. Because if you miss even a single one, that's the one the adversary will magically manifest into the box. Then he'll just switch on that specific one at the end, it'll turn on, and then you've lost your soul forever. Okay, so clearly this is hard because you have to try all 2 to the n possibilities. But even if the adversary is honest with you and just straight up tells you this is the circuit in that box, if he gave you in advance the blueprint of the circuit so you could actually test it, you could compute all these possible configurations, even if you had that additional knowledge so he couldn't cheat you by just magically creating circuits at will, it's still going to be hard. So particularly, this is a problem called circuit SAT. It's the problem of trying to find any configuration or any inputs of 0 and 1s into the circuit so that the final output is 1. So the issue here is it's going to definitely take you 2 to the n time to solve this. And that's probably more than your lifespan. So 2 to the n, if n's like 100, is already incredibly huge. So what should you do? You don't play the game at all. You just reject the offer. So you tell the salesman no. Now the idea here is that maybe circuit SAT is solvable. We just don't know the answer to it. So maybe, just maybe, there exists a clever algorithm that just hasn't been discovered yet. So we can't formally prove there's no algorithm. We just have evidence there's none because no one's been able to solve it yet. So you're probably thinking maybe everyone before us is just dumb. I can solve this problem. Well, I ask you, even though we haven't proved there's no anti-gravity unicorns, we haven't proved it mathematically, but still probably isn't true. So you tell the salesman no, and then he smiles and flies away on his anti-gravity unicorn, never to be seen again. So any questions on this setup here? Is it clear why this problem is hard? Why you have to try everything? Yes?
The circuit has five. That's what I was thinking. Like it has five input versus the actual switches being 4. So
Yeah.
hard.
No, I just drew it that way. If it helps, I'll make them. I mean, at the beginning, he is cheating for sure. But after you call him out the first time, then he'll be honest. He'll be like, okay, here's the actual blueprint. I'm not doing anything tricky. But even if he gives you the blueprint, it's still hard. And that's the point. But the idea of why it's still hard is just because you literally have to try every possible configuration, because if you miss even one, that could have been the answer to the problem. Whereas for things like greedy algorithms, you can just ignore like a huge chunk of the possibilities for those problems. But here, it's not the case. You really have to try them all. So any questions on this? Okay.
What if there was a circuit? Could we like backwards?
So I'm assuming you're given a circuit. In the updated version, you're just given the circuit. You can actually see and interact with it. You can plug in numbers in, see what happens, whatever you want to do. And try to like invert it. So generally, you can't do that. Yeah, so the issue is for every choice here, you have to consider all possible choices of those input wires, and so on and so on. So there's going to be like 2 choices for this, 2 choices for this, and keeps stacking. So you could do that, but you're still essentially looking at 2 to the n possibilities. Right, because it's a logic gate, so these are all 0 and 1. Each wire has value 0 or 1. Yep. Okay. So you've probably heard of the P versus NP question before. So now we're going to talk about it rigorously. This is pretty much the main topics of like complexity theory. And if you solve the P versus NP problem, you're probably aware you'll get $1 million. But the $1 million kind of is irrelevant because if you can prove P equals NP, that means you have an algorithm to solve every problem ever. And so I'm pretty sure you'd be like the king of the world, literally. Like literally you could control the entire world at that point. So why? Who cares about $1 million? Yeah, so try to prove P equals NP, please. If you prove P does not equal NP, everyone will love you, but you won't have that much power over the world. It's very sad. Still get the mill, though. So what is P and NP? So now we're going to consider decision problems. So these are problems with yes or no answers. So for the circuit sat problem, it's a yes or no problem. It says, does there exist a setting of the input variables so that the output is 1? You don't actually have to compute the setting of it. You just have to tell me yes or no. And generally, we'll denote this by saying if A is a decision problem, then X is an A if X is a yes instance. You can also think of this as A of X equals 1. So this would be a yes instance. So it's an input to the problem that has answer yes. On the other hand, if you had X is not an A, that means it's an input to the problem that has answer no. So that would be, say, a circuit that has no way of getting a 1 out. Whereas this would be a circuit that, maybe if you put 1, 1, 1, 1, it becomes a 1 in its output. So those are decision problems. We've seen a bunch of decision problems before. You're doing one on the homework, which is, can we do the advertising scheme on the website? And so if we just restrict ourselves to decision problems, these are typically easier problems than a full optimization problem, because in those problems you have to solve, like physically find some complex quantity like a shortest path. Whereas here we just want to say yes or no, is there a shortest path of a certain length? So these generally are easier than the optimization versions of the problems. But if we can show these things are hard, obviously that would imply the full versions are hard, because it's easier to say yes or no than to actually give me some physical object. Yes?
So is it enough that we say it can be yes or no, or do you have to know if it's yes or no?
So the problem, every input to the problem has an answer that's yes or it's no. It's exactly one of them. You don't need to know what the answer is, just you need to know the problem is of that form. Yeah. So what the problem is asking you for has to have an answer that's a yes or no type question. So if we have a decision problem, we define P as the set of decision problems that can be solved in polynomial time. That's pretty much every single algorithm we've talked about in the class. Things that are like O of n to the 3 are example of poly time. Something like O of 2 to the n is exponential time, so that's bad. It's not poly time. And intuitively, P is the set of problems that can be solved quickly. So this is just a convention we use in algorithms, that poly time equals easy. You could definitely argue that's not true, because n cubed solutions are way slower than n log n solutions. So in practice, of course, you'd prefer an n log n solution. But the reason we focus on poly time is, at least usually, if you can get it to poly time for any polynomial, it could be huge, like n to the 100. Typically, there's follow-up research that leads to something smaller. So eventually, you get down to something more reasonable, like n cubed or n squared. But this is just something for scientific convenience. On the other hand, NP is the set of decision problems with a special property where it's easy to verify a solution. So if you gave me the answer, you told me the answer was yes, can we quickly check that the answer was truly yes? Is there a short proof that can tell us that fact? So for circuit sat, what's a short proof that it was a yes instance? It'd just be a specific setting of the variables. So here, in orange, the 0, 1, 1, 1, I guess I need another one now. This is a short proof that it's a satisfiable instance. Why can we check it efficiently? Well, for this reason. We can just plug in all the numbers on the inputs and then use a DFS/DP type thing to propagate the answers to the front. And then we can just check, was the output equal to 1 or not? So if I know the circuit and you give me the solution, which is this setting of variables, it's easy to check that that was indeed a solution. But if you don't give me the solution, it's totally arbitrary, and I have to find it, then it's harder. So intuitively, you can think of this as a needle in a haystack. So if I gave you a needle, you can easily check it's a needle. So that part's easy. But if I just tell you there's a needle in the stack, how are you going to find it? So you should think of this kind of like what we did with the recursion fairy. So there we had this all-powerful fairy who could solve some problem for us. And then given that solution, we do something else. So here, if we wanted to solve the whole problem, we could have someone else who's more powerful than us find the needle. They give us the needle. We can easily check it is a needle. and then output it. So checking the solution is correct is easy. We know how to tell a needle's a needle. But actually finding it, sifting through all the hay to find it is hard. So that's the idea behind an NP problem. If you gave me the solution, I can, in polytime, check it is a correct solution. But if you just gave me the problem with no hints at where the solution is, I'm stuck just looking through every single piece of hay. And so it's going to be exponential time. So the exception to this is if you have some kind of magnet to help you. So if you have a magnet, well then it's just going to suck the needle right out of the haystack. And you can think of these magnets as those problem-solving techniques we started off with. So DP is a magnet. Divide and conquer is a magnet. They're all tools to help you remove a bunch of the hay so you can find the needle quickly. But sometimes the haystack is too complex, and then none of those approaches will work. So a good example of this is the Eulerian circuit problem. So if you saw the video about Eulerian circuit, it's a really complicated problem, but you can end up solving it in linear time. It's super fast. On the other hand, the Hamiltonian cycle problem, which is almost the exact same problem, is hard to solve. So they're almost the same problem, but one's a linear time and one is we don't know how to solve it. It's so hard. So that's an example of magnets and how to use them to find the needles. So another example of this, solving versus verifying, would be like a homework problem. So if I give you the answer to the homework, then it's usually easy to check it's correct. So think of how many times you looked at the solution after the homework was due, you read it and you're like, oh, that totally makes sense, why didn't I think of that? Right? On the other hand, actually coming up with the solution, finding the answer on your own, is very hard. So here's an example of that in real life. It's easy for you to check that this all makes sense, that this solution's correct. But if you had to actually come up with the solution, well, that's taking you almost a week every week to solve that. So the idea here is, can creativity be automated? So if P equals NP, what that's saying is verifying and solving are the same. So given a computer, there exists an algorithm that could solve the homework for you, not just check it was correct. There are algorithms that can prove theorems for you, which would be kind of crazy. It basically kills all creativity. Computers can just do everything for us. But most people don't think P equals NP. So in particular, most researchers think this is what it looks like. You have P, the easy problems, is somewhere inside the intersection of co-NP and NP, and that P and NP are strictly different. So co-NP is like the opposite of NP. So instead of checking easily that a yes answer is correct, it's checking easily that a no answer is a no, which is typically weirder. It's a little weird to check that there is no solution quickly, because how do you do that without, looking through all answers? But there are problems that are like that. So that's what co-NP is, but not super important. So any questions about this idea of, what's P versus NP really about?
When you say P equals to NP, are we discussing with respect to a specific problem or in general?
These are sets. So it's saying the two sets are equal. So it would mean every NP problem has a efficient algorithm to solve it.
So basically, if I'm asking the question of whether P equals to NP, I'm really saying whether solving a problem is equals to verifying it for any kind of problem.
Yeah. Yeah. So,
that we know is not true, right?
Well, we don't know it's not true.
We can just come up with one concrete example.
but we can't. It feels like that, right? But we can't actually prove it. Yes?
Is there an overlap between the co-NP and the NP problems that is not the P problems, and how are those not P if we can check yes and check no?
Yeah, so this area right here that's in the intersection but not P is conjectured to be different. So it's not, so P is not conjectured to be equal to NP intersect co-NP. There's something called Latner's theorem. There's a bunch of theorems, really, that give you really weird examples of problems that would be in the middle between NP and P, assuming they're different. So these are all conditional. So if we know P is not equal to NP, then this problem in between exists. But it assumes P does not equal NP. So if P does equal to NP, then obviously there's nothing in between. It doesn't. This is just about verifying it quickly. So this is saying if P is the intersection, that's saying every problem that can both be checked for a yes quickly and be checked for a no quickly are in P. You can do both. There's an algorithm for both sides. Yeah. So remember, P, you're solving the problem, right? So you can tell if it's a yes or a no by just solving the entire problem and giving the answer. Whereas NP, you can solve one side of the answer. You can tell me, yeah, there exists a solution, but you have no idea how to tell me, no, there's none. Co-NP is the other side. So maybe I should draw a picture of this. So every problem is either a yes or no. If you can do both, it's P. Otherwise, it's like this. So do you have an algorithm to check this condition? Do you have an algorithm to check if this is a yes instance? Great, it's an NP. If you have an algorithm to check it's a no instance, that's co-NP. And if you have an algorithm to do both, then it's basically P. Or it's in the middle, but yeah. Yes?
So are we saying that so like for an NP question, are we saying that the algorithm to calculate the no answer is a non-polynomial algorithm, or just doesn't exist?
Yeah, non-polynomial time. They usually exist, right? Because you could just check every possibility of an input and just brute force check, is it no or not? Or is it yes or not? Yeah, so generally when we're talking about complexity theory, it's about showing things are fast, not that they're solvable at all. But there's a similar theory about solvability called undecidability. It's like the same thing we're going to talk about today, but instead of running time, it's just can you solve it ever? But that is a topic for 5:20, so I won't go into it. If you have questions, feel free to come to office hours, because I used to study that. Okay. So that's the P versus NP question. Now let's talk about completeness. So this is where it gets really weird. So a problem is called NP-hard if a polytime algorithm for pi would imply a polytime algorithm for every single problem in NP. So pi is NP-hard if solving pi implies all of P equals all of NP. So if you can solve this one problem efficiently, then there's a way to solve every single problem in this class efficiently. So it's a super strong condition, and it's going to get even stronger in a second. What this really means is actually crazy, but just definitions right now. So pi is NP complete if pi is in NP and it's hard. So in general, this picture here, NP hard problems are just everything that's above NP and including the tip. So it's pretty much like every problem basically. It's the majority of problems. But this slice here, this green slice, that's the NP complete problems. So they're both NP hard and they're in NP. That little sliver right there. So we're going to focus mostly on hardness in this class, but the hard part is showing that it's hard. So once you know it's hard, showing it's in NP is pretty easy. So that's why we're going to focus on this part. Okay, so what this means, what it'll actually mean for us, is if there's an algorithm for pi, we can convert that algorithm into a different algorithm that solves any other given NP problem. So we have a general method of taking an algorithm for this problem and turning it into an algorithm for any other problem. So that's the actual crazy part. We take A, take alg for pi, and there's a general mechanical procedure that outputs some f of alg that can solve any given problem pi prime. So this is already crazy, but this is even crazier. So not only can you actually solve it efficiently, but here's the exact way to solve it. We have a mechanical way to actually give you the new algorithm. So quite literally, if you solved any of these problems, we instantly have solutions to all of them. Because we can take your algorithm, plug it into this black box function f, and then we get an algorithm for whatever problem you wanted. Yes?
So NP-hard problems can be non-NP?
Yep. It's anything in NP or higher.
But by definition of NP, it is a problem that's that hard that should be NP, right? How can there be a problem which is NP hard but not NP?
Exponential time algorithms?
They will not be NP.
Not necessarily. We don't know if NP equals exp, but what we definitely know is NP does not equal double exp. So anything of the form 2 to the 2 to the n, that's double exp. And this does not equal exp. And NP is a subset of just single exp. So we know for sure there's plenty of problems that are, like there's problems that are just unsolvable too. Those aren't in NP, of course. There's a huge category of problems that aren't in NP. But anything in NP or higher is called NP-hard. So for example, this would include P space. These are just things that can be solved in polynomial space instead of time. Space generally is a stronger resource than time. So that includes everything in NP, and you can actually prove that. Provably, we know it's all in there. There's also more complicated things like randomized polynomial time, PP. That's also provably stronger than NP. Things like post-quantum with superposition, it's called post-BQP SLR. That also contains NP. But yeah, so there's plenty of things bigger than NP. In fact, there's a whole hierarchy called the polytime hierarchy that's all just NP, and then you keep stacking higher and higher. Yes?
So basically, we are not solving the problems, but we're like theorizing.
Yeah, we're classifying them. Yeah. Yes?
Has anyone ever thought that they solved an NP-hard problem, but it turned out it wasn't NP-hard?
Oh yeah, I've done that. Everyone's done that. Yes.
What is pi prime represent?
Pi prime is just a different problem. So you give me any other problem pi prime in NP, and we can solve it if we can solve the NP complete problem pi.
So is it a different version of pi? Or is it
No, it's just a completely different problem.
Oh, okay.
Just any other problem that is in NP. Any of them. That's why it's so crazy. Yes.
How can we say that all NP problems are equivalent? Like,
We'll talk about that formally in a second. This is just going through the idea for now. The answer is reductions. So, yeah. Yep.
Wait,
a polynomial time algorithm?
NP-hard is a class of problems, just like NP.
But you can solve them in polynomial time?
No. The idea is if you can solve any single problem that's NP-hard in polytime, then you can solve all of them. It's a set of problems that are basically equivalent to each other. If you can solve one, then you can solve all of them. You can define this idea for any class. So you could define something called P-hard, which just says if you can solve this fast, then you can solve everything in P fast. That's trivially, P-hard is just all of P, right? Because
Then you can't solve NP problem in polynomial.
yeah, we don't think so. So that's the next step. Yeah, this is a way of proving things are not solvable. Yeah. So consider this statement. If I own a dog, then it can speak English. So this has a natural takeaway. There's something you should infer from this statement, that I probably don't have a dog. Right? So if I have an if-then statement, and the if part is clearly, or the conclusion is false, the only way for the overall thing to be true is for the assumption to be false. So if you have P implies Q, and Q is clearly false, for the implication to be true, you need that P is also false. But you can just think of this intuitively, right? If I said I own a dog, then I can speak English, then you probably don't think I have a dog. That's more likely than me having a dog that speaks English. And so similarly, if a problem is NP-hard, you should not believe it can be solved in polynomial time. So this gives us evidence that we cannot solve a problem. Because if we could solve it, then we could solve all of these problems that people have failed to solve over the last like 100 years. That's pretty good evidence. Just like how, technically we've never seen an anti-gravity unicorn, we have pretty good evidence that it doesn't exist. So any questions about that? That's basically the conclusion. If you show something is NP-hard, then it probably can't be solved efficiently. That gives us good evidence.
Is that what makes it by classification?
Yeah.
And then you might have mentioned this, but the NP-complete, what would that classification?
So NP-complete is NP-hard and in NP. So you can think of it as the hardest problems in NP.
So would they, since it's in both, would it also be true to not believe that it can be solved?
Yeah, exactly. It's the same thing. Yeah, typically we focus on NP-complete problems because NP-hard problems are like almost everything, so like it's not very useful. But NP-complete, those are problems that you actually see and want to solve but can't, so it sucks. Like traveling salesman problem is an example. So the traveling salesman problem, if you haven't heard of it, it's basically Hamiltonian cycle, which is something we've basically considered in the course already. So we've already seen examples of problems that are basically in this class, and they are unsolvable. So the point here is we can't, say for sure that P does not equal NP, but what we can do is give a conditional lower bound. So it's not a true lower bound. We can't say this problem takes exponential time, but we can say if it is possible to solve it, then we could solve everything. And so it's unlikely we can solve it. So the condition here says if we could solve it, then we could solve pretty much everything. So it's unlikely solvable. Okay, so we can't actually prove these are slow, but what we can do is say it's at the very least as slow as some other problem. So we can keep building up a set of problems that are all slower than each other or roughly in the same ballpark. And so if you proved any one of them was slow, you prove all of them are slow. If you prove any of them are fast, you prove all of them are fast. So we're just grouping problems together and treating them together to give us more evidence that they're either solvable or not. Yes?
Do there exist more clubs of unsolvable problems?
Oh, yeah.
All of them in this?
No, there's other ones. So there's subsets of NP that we think are also hard to solve, like BQP. So most people think quantum computers can solve problems that classical ones can't. So like BQP would be somewhere in the middle. There's other things like randomized algorithms. Some people think you can't de-randomize, so then the randomized class RP would also be in the middle. Things like that. I could make this picture like 1,000 times more complicated, which I'm happy to do in office hours because it's really fun, but we don't really need them right now. So any questions on what a conditional lower bound is about? So it says conditional on one problem being hard, then all of them are hard. So it simplifies our problem from proving every single problem individually is hard. We reduce it to the easier problem of showing just this single problem is hard. One of the NP-complete problems. So the question is, yes?
So to show that a problem is hard, that takes polynomial time to do that?
To show a problem is hard is a proof. It's not an algorithm. So it's constant time, I guess, if you want to think of it like that. Yeah. So showing something is hard is a mathematical statement. It's not, you're not actually doing anything to the problem. Yes? Yeah, I think it'll help to see the actual definition. This is just like the high-level idea, which we'll see in a second. But the first thing is, do hard problems exist? Because if there's no hard problems we know of, then this whole thing is meaningless. So the Cook-Levin theorem says that circuit sat, which is the problem we considered with the light bulb, that's actually NP-hard. So there's at least one problem that you could use to solve every other problem in NP. And the idea kind of makes sense, right? Like every day we use a general purpose computer, those are built off of circuits. And you're doing things like playing Halo on your computer, that's like super complicated, right? Any video game's super complicated. But you're doing that just off of circuits. Like using circuits alone, you can do so much. Like watching YouTube is not easy. There's so many like pixels and streaming and stuff. It's really complicated. So intuitively, just from our everyday life, it should make sense that this would be an NP-hard problem because we can represent almost any function using a circuit if it's complicated enough. So if you could solve the circuit sat problem, you could think of as building out of circuits some kind of structure representing your problem, and then you just feed in that to the circuit sat problem to solve yours. But the point is these problems do exist, which is kind of crazy, because it's a really strong condition. So let me talk about the formal definitions now before we pause for more questions. So formally, the way we're going to talk about hardness is through reductions. And these are the real reductions. So we've talked about reductions a bunch of times in the course to prepare you for this moment, basically. So we've talked about recursion as a form of reduction. Graph reductions are a form of reduction. But here's the most general version. So if you have a decision problem A, we say A polytime mapping reduces to a decision problem B, and that's denoted like this. So A less than or equal to B, but now there's a P and an M to indicate it's polytime and it's a mapping reduction. So A is polytime mapping reducible to B if there exists a polytime computable function f that converts or transforms inputs to the problem A into inputs of the problem B with the following property. If little a was a yes instance to problem A, this should happen if and only if f of A, which is an instance to B, is a yes instance to the problem B. So the takeaway here is we can convert one problem into the another so that answers to one problem are equivalent to answers to the other problem. So answers of the two problems are equivalent under F. So if A, little a, was a yes instance, we need f of A to be a yes instance of the other problem. So for circuit sat, you could think of, if you're reducing anything to circuit sat, you would need that problem to have a yes instance if and only if the circuit you create can be satisfied, and vice versa, if the circuit you create is satisfiable, that should imply the original problem was a yes instance. So you can think of this as a way to solve problem A using B. You just take your transformation f, you throw A into the transformation, then you solve the problem given a B algorithm. So an algorithm for problem B, you just plug in f of A into, and then whatever it outputs is your output. So you could think of this as you have this box here. This is an alg for B. You take your instance A, you turn it into f of A. F of A goes into the algorithm for B, and whatever the answer is your answer. So it's basically a reduction. You're solving problem A using problem B as a black box. And it's a particularly simple reduction. You're taking the answer B gives you as your answer. All you have to do is turn A into f of A. That's the only thing you have to do. So these are mapping reductions. Any questions on a mapping reduction? It's called that because you're mapping your input into a different input to plug into the algorithm for the other problem. So in general, you don't really need to create mapping reductions, but I think it's easier to define mathematically what it is. Usually you're going to be doing Turing reductions, which are intuitive, but you can't really define it mathematically in an easy way, like here. So a general polytime Turing reduction, which does not have the little m there, it's just A less than or equal to sub P of B. This just means you can build a polytime algorithm for A that uses an instantaneous algorithm for B as a black box. So here's a little picture. The whole thing here is an algorithm for A. And what it does is it takes as input, little a. It does some stuff, and eventually it creates some input to problem B. It gets the answer, does more stuff, and we'll just repeat this process. So it's going to do whatever stuff it needs to do. Then maybe it needs to ask a question about B problems. It does. It uses the answer to do more stuff. So you could think of this like merge sort. In merge sort, we reduce to the merging of the sorting of the two halves. So that's the B step, is we sort the left half. We get that answer, we sort the right half, we get that answer, and then we do the merge. And then that's our final answer at the end. So merge sort is one example of this. Here B would correspond to sorting 1/2 of the array. And stuff is merging. Okay. So any questions on what A reducing to B in polytime means? Yes.
Is this what we were doing in discussion yesterday?
Yes. I hope. And in general, when we're doing graph reductions, when we're doing max flow reductions, pretty much everything we've done in the course, other than, pretty much everything, is of this form. We solve a problem by using another problem as a black box. Okay, so now here's the important part. This is where the NP-Hardness comes in. So if A reduces to B in polytime, and B, the problem on the right, is in P, then A is in P. So that's easiness. That's what we've been doing throughout the course, right? So we solve a problem by reducing to another problem we know how to solve. So maybe B here would be like whatever for search on some graph, and we're using that search to solve some other problem, like racetrack. So that's typically what we've done throughout the course. We use one problem to solve the other. But we can actually flip this around. So if the first problem is hard, then the second problem is hard. And in general, just note that reductions are transitive. So if A reduces to B and B reduces to C, then A also reduces to C. And you can see that by basically composing the two reductions. So if you had a function f converting problems of A to B and a function g converting problems from B to C, then f of g is going to give you a way to convert A to C. But not super important, just for your information. Okay, so why is this true? What's the idea? Well, if B is in P, and we have a black box for B, a black box for P gives us a solution to A, then the algorithm for A that we created using B is polytime. So like if we look at this picture here, if doing all this stuff is polytime, this is like n cubed, and if doing the stuff in B is also polytime, maybe it's like n to the 5th, then no matter what we do, maybe we're multiplying those times, maybe we're composing them, no matter what, it's still polytime. So here, if the black box took n to the 5th time, and we used it 6 times in some like crazy for loop, well, overall, it's going to be n to the 30, which is, it's very large, but it's still a polynomial. So if B is fast, and we can use a black box for B to solve A, well, then that algorithm is also fast. Okay, so any questions on this? This is what we've been doing like all semester. This is like when you run whatever for search on your new graph, you have to convert the running time in terms of the original input. So you say like, oh, the new graph E prime V prime, that's really size n squared, where n is the original problem size. And so the whole problem will be like n to the 4th or something. But it's still polytime. Okay, so that part's the easier part. That's what we've been doing. So now what's the hard part? So intuitively, you could think of this first in terms of contradiction. So if B was in P, or if it's anything that's not NP-hard, so let's call it NP-easy. So if we could solve B, then part 1 implies that we could solve A. But this contradicts the fact that B was hard to, or sorry, that A was hard to solve. So if A is hard to solve and B was easy, we get a contradiction because of part 1. So if A is hard to solve, that immediately tells us that B is hard to solve. That's how you think of it from a contradiction perspective. You can also think of it just by the transitivity property, which is the way it's actually proven. Take any problem in NP. If A is NP hard, then we know that C polytime reduces to A. So we could solve C using a black box for A. That's what it means for A to be NP hard. This is the actual definition of NP hard. Does that clarify slightly?
Okay, so if an NP problem can be solved by using A, then A is an NP hard.
But it has to be for every problem. That's the key part.
Every NP problem?
For every single NP problem, you can convert it into you can solve it using A.
So every single NP problems can be solved by that single NP hard.
Yep.
And no matter what type of NP problem.
Yep.
Oh, because NP problems are exponential.
That's not important. This is just a relative thing.
But if there was suppose one C which could be solved by A, then A might be NP hard or NP, right?
If there's one problem C that can be solved,
Using some other problem that's A,
yeah.
then we can't say whether A is NP or NP hard. It can be either, right?
This just defines hardness. This just says it's NP hard. It does not say that A is in NP. That's a separate thing. So this just tells you that A is at least as hard as every problem in NP. And that's literally how you should read this statement. For every problem in NP, that problem is less hard than A. A is harder than every single problem in NP. And that's why it's called NP hard.
So the circuit problem you mentioned earlier, you said it was NP hard.
Yep.
Then using that
If you could solve it, yeah.
If you could solve it using that algorithm, you could solve all NP problems.
Yep. That's why it's crazy. So if I told you, if I gave you a box and said, in this box is an algorithm to solve circuits at, then you could take that box, manipulate your input to whatever problem you care about, so that you could solve that original problem using that box.
Could you only solve circuit problems using that?
Nope. You can solve anything. We'll see an example. It's crazy. We can convert, say, like a graph problem to a circuit problem. We can convert, and vice versa. We can convert like subset sum, number problems into circuits. We can convert Mario Bros into circuits. That was that thing I showed you at the beginning of class, basically. Yeah, so it's very crazy. Yeah.
That makes sense though, that circuits, everything can be turned into circuits.
Right. Yes. So that's that proof. So this is the Cook-Levin theorem, which is very complicated. It is not easy to do it. This was like a super famous theorem that took a lot of work to do. So the idea is, given any problem, you look at its binary expansion, you convert it into binary somehow, and then you do this very complicated conversion from the binary into circuits. That's the idea. It is very complicated, so if you want to see a proof, check out 520, because I think they sometimes prove it in 520. They definitely prove it in 720, if anyone cares. But it is hard. It's very hard. So that's why, in general, you don't have to prove this. Like, it's proven for you. Now all you have to do to prove a problem is hard is use a reduction. So that's why this is really cool. Anyway, so the reason why transitivity implies something's NP hard is if we know every problem reduces to A, And by transitivity, A reduces to B, that means every problem in NP also reduces to B. And so B is NP-hard. Yes?
So when we do the reduction, are we saying that, like, so for C to A, are we saying that A is easier to solve than C or harder to solve than C?
C is easier to solve than A.
Okay, but we have some sort of black box function that solves A for us.
Yep. The whole point of this, it's conditional, right? Assuming we have an algorithm for A, we get one for C. So when we flip it to do the contradiction or the contrapositive, that gives us the opposite. So if we had a way to solve B, we could solve A. Implies if we can't solve A, we can't solve B. So you can flip that statement. So what's the takeaway? If you want to show something's NP-hard, did I already say this? No, I didn't. Okay, cool. So let's say you want to show problem B is NP-hard. Then reduce a known NP-hard problem to A, or sorry, from A. So that's all you have to do. You don't have to go through all the work of showing every single thing can be solved by it. You just have to show a single one can be solved with your problem B. Now just note that this is the opposite of what we've been doing in the course so far. So generally, when we're reducing A to B, B is the problem we already know how to solve, and we're using it to solve A. But when we're doing NP-hardness, A is the problem we know how to not solve, and we're using that to show B can't be solved. So the direction is swapped. For polytime, B is what we know how to do. For NP-hardness, A is what we know. So it's important to keep that direction of the reduction clear in your mind. But we'll see lots of examples. Yes?
So NP problems and co-NP problems, they are polynomial time?
No. We don't think they are.
Oh.
Yeah. We think P is different from NP.
Okay, so P is polynomial.
Yep.
All polynomial answers that are like concrete are
All problems we can solve in polytime.
polytime are P, and then NP can be polynomial and not polynomial. I mean exponential.
NP, we think the problems are exponential to solve in general, but they have the special property that you can check answers in polynomial time. So if I gave you the answer, you could check it fast, but you can't find it fast.
Oh, okay.
Yeah.
And then NP-hard problems are just unsolved.
NP-hard are just problems that can solve every NP problem.
But they're unsolved.
Yeah, any problem that's NP-hard we don't know how to solve in polytime.
In polytime.
Yeah.
But it's possible to explain.
It is possible. It's possible they're solvable, it's possible they're not solvable.
Okay.
But this just gives us evidence that they're probably not solvable. Because there's so many of them that we don't know how to solve.
Okay. And then for NP-hard problems, like, are there like a lot of like?
Yeah.
So you have to prove that it is an NP-hard problem to say that it's an NP-hard problem.
Yeah, you have to prove it first, yeah.
And that takes a lot of work.
Well, the very first one took a lot of work, but now all you have to do is do a single reduction to prove it because of the transitivity. So if you have one problem that's NP-hard and it reduces to whatever problem you care about, immediately that problem's NP-hard. So that's this thing here written in green.
Okay. So we would need to know like multiple NP-hard problems in order to prove. So we
More
need to
are.
know like proved NP-hard problems to prove that.
New ones are.
NP-hard problems.
Yeah.
So this statement says basically we have to reduce the known NPR problem, that is A, to B.
Yep.
So B is NPR.
Exactly. Yep. Yes.
I think that kind of answers my question, but basically, if we do this, then we're saying that every problem in B is NP-hard, or just that one specific problem that we mapped?
So B is a problem. It's a set of instances, like a set of graphs with some property you want. You want to show solving that problem is hard, and you do it by converting instances, specific instances of the problem, into another problem. So, for example, to prove a reduction, you have to prove that A is a yes instance of A, implies that f of A is a yes instance to B, and f of A is in B implies A was a yes instance to A.
So it's just on an instance-by-instance basis. It doesn't apply to the entire problem.
Yeah, but you should think of this as giving an algorithm for A that uses B as a black box, as a subroutine. So I wouldn't stress too much about like instance to instance. Just think of how can we use B to solve A.
Yeah. So like, given any input, then we can solve A. Or like
Yeah, we can figure out whether A is a yes instance by using the black box for B. Yeah.
Can you rephrase that green statement? Like it's not clear just by green statement. So basically, it should say that we have to reduce a known NP-hard problem that is A to B.
So that's why I said from. And I'm phrasing it this way, even if it's a little more unclear, because that's how everybody does it. So I want you to get like exposure. But to like write out what's happening, this is what you're showing. That's what you're proving. Where A is NP-hard. So that's what you have to do. Okay, let's go through some examples because I think that'll make it clear. We'll start with a really easy one. So we know that circuit SAT's hard, but circuits and Boolean expressions are pretty similar. So let's consider the formula satisfiability problem, which is called SAT, and you're just given some Boolean formula like A or B or C or not D, if and only if B and not C, etc., etc. Just some giant logical expression. And the question is whether you can pick Boolean values to the variables, so like pick A as 1, pick B as 0, etc. Or you can think of them as true, false, same thing. We'll usually talk about them as 0, 1, but they're the same. So you want to pick values of the expression so that the entire formula is true. So it's literally just circuit SAT, but with a formula instead of a circuit. So how do we show SAT is NP-hard? We're going to reduce from circuit SAT. So we're going to solve circuit SAT using a SAT solver. So this is the weird part, because usually the thing we know how to do would be on the right side. But here it's the thing we want to prove stuff about that's on the right side. So how do we do this? Well, we can convert a circuit into an equivalent formula in polytime. So given a circuit K, we need to transform it into a formula phi. So for example, if we did this circuit from before, what we can do is let each wire be represented by a logical variable. And then what we can do is just use whatever these gates are to define a formula for the wire. So for example, this is an AND gate. So the value of Y1, the thing that exits that gate, is just X1 and X4. That's just the definition of what an AND gate does. So because that's an AND gate, the output of that wire will be Y1 equals X1 and X4. And then we just keep doing this. We just define whatever the Y's are based on the type of gate that produces it and whatever the two inputs were. So y4 would be y1 or x2, because those are the two inputs and it's an OR gate. So we can just describe in terms of a logical formula what each of the wire outputs are inside the circuit. And then finally, the output of the circuit is this variable C. And so at the very end, if we want the output for the whole circuit to be 1, the whole output's 1, then this variable Z has to be 1. So we have to AND this whole thing with Z. So basically it says each of these wires is correctly corresponding to their gate, and the final output was 1. So this is going to be 1 only if this is 1. So any questions about this? You don't need to know this in like super detail, as long as the idea kind of makes sense. We can convert circuits into Boolean formulas just by literally saying in terms of logic, what will the outputs be at each step. And also, it's important that we do this in polytime, the conversion. And clearly, this is like linear time because we just go through each gate. We touch it once to compute the corresponding formula. Each gate, we touch it, make the formula, and so on. So overall, it's going to be very efficient to compute the output formula. Okay? So we can convert a general circuit into a formula that's equivalent in linear time. But now the question is, are they really equivalent? I could just be making that up. So to formally prove the reduction is correct, we have to prove that the circuit K is satisfiable, i.e., it was a yes instance, if and only if the formula we constructed, phi, is also satisfiable. So one should be a yes instance exactly when the other is a yes instance. So the high-level idea behind the proof is if we had a set of inputs that satisfied circuit K, then that turns into an assignment for the formula phi by computing the outputs of every gate and making those the y variables. Okay, so if that wasn't clear, here's the exact math which says that. So if there exists an input, a setting of the x's, so that your circuit evaluates to 1, then we're going to inductively define the value of these variables y such that yi is equal to yj and yk if yi corresponded to an AND gate with inputs yj and yk. So if we had this. Or you could think of it as we computed all the gates values in the circuit and just plug those values into the y variables. It's the same thing. So if we do this, then we know the output of every gate exactly matches the variable y's. And so essentially we've simulated the flow of bit values through the circuit using the formula. And because of that, if we plugged in those x's and the computed y's into our formula phi, we know it's going to be 1. Because the variable z, which I forgot about, the variable z is 1 because k is 1. And the rest of the formula just says that this gate equals these input values, the AND of these input values, or the OR. Okay? So that's formally how you would basically prove that. Now the other direction's even easier. So if I had an assignment for formula phi, so some setting of x, y, and z, we just ignore y and z. That's it. So we had some x, y, and z equals 1. Well, that immediately applies the same x1 through xn is equal to 1. Okay. And that's just by how we construct the formula. So the reduction's correct. That proves the reduction's correct. We know it runs in poly time. And so SAT is NP-hard. And now another way to visualize the reduction, instead of converting one problem into the other, we could think of it as using a magical black box for SAT. And you know it's magic because there's a rainbow there. We can use this magical black box for SAT to solve circuit SAT problem by just taking the input k. We transform it in linear time into the formula phi. We plug phi into the SAT algorithm, and we just keep the same answer. So if SAT said true, we output true. If SAT said false, we output false. Another way to see that is by the pseudocode. We turn k into the formula phi, and then we magically run SAT of phi. These are equivalent. So if we could solve the SAT problem, then this gives us an efficient algorithm for the circuit SAT problem. And so since we know circuit SAT can't be solved efficiently, or at least we think so, this implies we can't solve SAT efficiently. So any questions about this? It's not super important that you know the exact details of this reduction, because it's like weird logic, but yes.
Could you go over again why this is in polynomial time?
Yeah, so the way the formula is constructed is for each gate, we compute the output of the gate, and we make an equivalent formula expression. So I'm going to loop through every gate in the circuit, bottom up. I start closer to the inputs. And I make this formula, y1, based on the two inputs. So for each gate, I do constant time. I take a couple of the inputs, 2 specifically because it's a binary circuit, and I make a little formula for it. So for each gate, we make a small formula for it, and then we just slap an extra variable z at the end. So it's basically O of 1 time for each gate, and so that's linear time because the size of a circuit is the sum of the gates, the number of gates. So that's why it's linear time. You could think of it as basically doing a depth first search, and you're computing the formulas once you hit the bottom, and you propagate them up. It's linear time to do the conversion. Remember, we're converting the circuit into a formula. There are no solutions here. You only care about the solutions when you're proving something's in NP. But we're not going to do this in this class. You just have to worry about proving it's hard.
So, wait, to prove that it's hard, it takes linear time to do that, or constant time?
The proof is just a proof, but the conversion algorithm takes linear time.
Okay, but that's just for this case. But like in general, it's usually polynomial time, or
Yeah, for this specific problem, this specific reduction, it's linear time, but in general, it could be huge. So for the actual Cook-Levin theorem, it's like n to the 100 or something. It's really big. Yes? Yep. Yep. So remember, these are the opposite of what we've done previously in the course. We want to show SAT is hard basically by contradiction. We know circuit SAT is hard, so if we could solve SAT efficiently, and there's a reduction, that implies we can solve circuit SAT efficiently, which is a contradiction. So that's why SAT is on the right side of the reduction, not the left side. If we swapped it, that would be saying we can solve SAT using circuit SAT, but we already know that because it's NP-hard. So that's not telling us anything else. So let me just write that down.
Also, you have to do it in that direction.
Yes, it's critical. So if we did this instead, this implies nothing new because circuit SAT is NP-hard.
Wouldn't that prove that SAT is NP-hard?
Nope. This says we used a hard problem to solve an easier problem. All this says is SAT is easier than circuit SAT. Doesn't tell us it's harder.
Wait, but if we're using circuit SAT, if you're using circuit SAT to solve SAT, doesn't that mean circuit SAT is the simpler problem? Because it's
Don't think of it like that.
like,
Usually,
I was
yes.
thinking about like the entire time.
Usually, yes, when you're trying to actually solve a problem, usually it's an easier problem. But when we're doing hardness, it's not. It's the opposite. Think of it as this is the more general problem. The thing on the right side is more general or harder.
Well, since it covers a broader scale, it's harder, I guess.
Yeah, kind of. So intuitively, you want to think of it as saying this problem is no harder than this problem.
Well then, I thought every problem could be turned, every NP-hard problem can be turned into a circuit SAT problem. Wouldn't
Yeah.
that make it the most general question?
It's the most general question in NP.
Just NP.
Yeah, because it's NP complete. It's also in NP.
So not the most out of NP-hard.
Yeah, 'cause the point of NP hard is they're all basically equivalent. None of them are like harder than the other. They're all basically equal. So here what this says is SAT can be reduced to circuit SAT, but we already knew that because it's NP hard. We can reduce anything to circuit SAT. It's not surprising. If we swap it, that's what's surprising, because then we're saying the hard problem can be solved by SAT, and so SAT is also hard. So this is not useful. So if you want to prove a problem's hard, you show it's harder than a hard problem. That's why we reduced it the other way. So what we did do was we showed circuit SAT reduces to SAT. And so because circuit SAT was hard, and this means harder than, this implies SAT is hard. So SAT is harder than a hard problem, and so by transitivity of hardness, SAT is hard. That's another way you can look at it. Yes?
Could you go back to the transformation step? So I'm just wondering, like, so to do these kind of problems, I reckon the hardest step is to do the transformation.
Yeah, that's the whole, yeah.
Okay.
The transformation and the proof.
Okay.
But the proof is going to be like basically
Nope. So let's look at another example. I think this one, okay, so this one we're going to actually think about the details of the reduction. I kind of try to skip them for SAT because it's boring, but these will actually spell them all out. So we've talked about this problem before, max independent set. So a k-independent set is an edgeless subgraph of G of size k. And so that just means it's some subgraph with k vertices, and for every pair of vertices, there's no edge. So the picture would look like this. Inside the subgraph, there's no edges between these nodes. That's why they're called independent. They don't touch each other. But it could still have edges to the rest of the graph. We don't care if there's edges touching the rest. We just care there's no edges in here. We don't want any edges like this. So you might remember we solved this using dp for trees, but now this is the general case. It doesn't have to be a tree. There could be cycles. And so let's prove it's actually hard. Independent set is NP-hard. And the way we're going to do this is by reducing from 3-sat. And 3-sat is just sat where the formula is in a special form called conjunctive normal form. And it has 3 literals per clause. So what this means is our formula phi looks like this, where these are all clauses. A clause is just a bunch of ors. And then you connect clauses with ands. So you have a bunch of ands of clauses, and each clause is just a bunch of ors of literals. And a literal is either a variable, like b, or its negation, like negative b, or not b. That's what a literal is. And now for a 3-sat formula, each clause has to have 3 things in it. There's 3 literals per clause, so there's 3 things you're oring, and then you could have unlimited number of things you're anding outside. So in particular, these 2 in the middle, those are 3 CNF, but these 2 are not, because the number of things being ored is too large. There are 4 literals in that clause and 2 in the other clause. So basically we have some kind of and of ors, and of ors of the or from j equals 1 to 3 of whatever literal is in that clause. That's generally what it'll look like. So any question on what this means? What does a 3 CNF formula look like? Yes.
Understood that the reset problems are clauses that have 3 literals.
In a 3 CNF formula, every clause has exactly 3 literals. There's exactly 3 things that are being ored together.
So we're converting everything into 3 literals?
No, we're assuming we're given a formula of this form.
Oh, of where everything.
Yeah.
Okay.
So to prove 3-sat is NP-hard, you reduce sat to it, and the way you do it is by converting the formula into a formula with 3 per clause. And there's a general way to do that, which I'm not going to discuss because it's incredibly boring, but you can read about it if you care. So you should know that 3-sat is NP-hard. You can reduce sat to it. So given any formula, you can convert it into a formula of this form with 3 literals per clause, and everything is anded between clauses. So this is the type of thing we're going to focus on. Formulas like this.
Wait, so we know that 3-sat is NP-hard, not sat?
They're both. So we just proved sat is NP-hard, and I'm telling you 3-sat's NP-hard.
Oh, okay, so we're assuming that sat is NP-hard, and since we can reduce from sat to 3-sat is also.
Yep.
Okay.
Yep. Any other questions? Okay, so how do we do this? So we're given a formula phi with 3 literals per clause, and we need to turn it into a graph and a number k in poly time. with the property that phi is satisfiable exactly when G has an independent set of size k. So here's the final proof we need to make. So let's keep this in mind. Always keep what you need to prove in mind when you're coming up with the reduction. So we're given phi, and we want it to be satisfiable exactly when the G we create and the k, just ignore that. That's kind of giving you an answer. And the k we create if G has an independent set of size k. So that's what we want to create G and k to satisfy. We're going to do this with an idea called gadgets. So in our graph, we want to construct little subgraphs, little pieces in the graph that somehow help us solve the original problem. So in particular, the goal of phi, of SAT, is to find an assignment of the input variables so that the overall formula is true. So essentially, we want nodes in the independent set to correspond to choices for the variables. And then we want the independent set to basically choose for us whether something's 0 or 1. So this is picking, say, a equals 1 or a equals 0. That's what we want to do. We need to find a way to solve the problem, SAT, 3SAT, using independent set as a black box. So this is what it's going to look like. We're given the formula, phi. We're going to transform it into some graph G and some k. And then we check, does G have an independent set of size k? If it does, we output true. If it doesn't, we output false. Now in this picture, this is specifically max independent set. But you could also do it for the decision version. Just, is there an independent set of size k? And that's what we're going to focus on. We're going to focus on the decision version. But you can also do it with the optimization version. But this is the idea. So let's think for a second how we might want to do this. So first of all, we have this nice number 3. 3 needs to help us somehow, because obviously if it wasn't helpful, I would have just reduced from SAT. So the 3 is useful somehow. So we know each clause has 3 literals. So maybe we can somehow turn literals into nodes and clauses into subgraphs. So let's try to turn each literal into a node and each clause into a subgraph. Okay, so each literal is a node, whatever, that's easy. But what's the subgraph we should be doing for the clauses? So each clause has 3 things. So our subgraph is going to have 3 things, 3 literals. And in general, you want to think of extremal cases, because that'll simplify your life. So what are the 2 extreme choices for this subgraph? Either it's completely disconnected, it is an independent set, or it's completely connected. It's the farthest thing from an independent set. Those will be the easiest choices. Now, if I made them edgeless, what would happen? Yeah, they're already an independent set, and so it's not really telling you anything useful. So that's probably not the right one. So the other option is making it fully connected. So we turn it into a triangle. So this is kind of helpful. So why is this helpful? Because if we include a node from this triangle in the independent set, we can't include the other ones. So let's say we include L1 in the independent set. Well, if we include either of the others, it's not independent because there's an edge between them. So what this does is it ensures we pick exactly one literal per clause in our independent set. So that's cool. That kind of helps, but even better, maybe we're picking that to be the true literal, and then it's really helping. So let's pick this, the thing in the independent set is going to be the true literal. So in the formula phi, this is the literal we make equal to 1. So we're going to make L1 equals to 1 in phi. Now we're not literally doing this, but this is what you want to think about. Somehow we're converting a solution, an independent set, to our new graph into a solution which is an assignment to the original phi. It's okay. So now we have a gadget for each clause. So this is going to be our clause gadget. So now we need to connect the clause gadgets together somehow, or maybe not at all. So what should we do for that? So once each clause becomes a triangle, we'll also add edges, u to v, if the literal at u is the negation of the literal at v. So in particular, if you had a and you had not a, you have an edge between them. Now, why do you do this? Well, let's say you chose both A and not A. If you chose both, based on the scheme I said above, we would be setting A to be equal to 1 and A not equal to 1, which is the same as saying A equals 0. So if we did that, we would have to set a variable to 0 and 1 simultaneously. But obviously that's not a valid assignment. An assignment is a single value that we associate with each variable. So adding those edges prevents that from happening. So those edges ensure it's a valid assignment. Each variable is either 1 or 0. And the triangle parts help us pick a single literal in each clause to be made true. And that's actually enough. That's all we need to do. So this is the graph we're constructing. Each clause is now a triangle. So here, A or B or C, that's this here. And there are edges between any node and its opposite as well. And highlighted in yellow is the independent set. So notice these 4 nodes, they do not touch each other. And so if we made them all true, so we make A true, so now the first clause is true. We make C true, or we make D bar true, not D is true, so that now that literal is true, that clause is true. C is true, so this one's true. And then A, again, is still true. So overall, the whole thing is true. So because there was an independent set of size 4, we were able to set each of the 4 clauses to be 1, and so the whole formula was 1. And the specific assignment that we created is built off of our solution, our independent set, for the graph we construct. What? Yeah, so we're using the independent set, if it exists, and converting it, or using it, to pick assignments of variables in phi. And in particular, if we have an independent set of size k, the specific choice of variables we pick will make it 1. So phi of x1 to xn will actually be equal to 1. So this is essentially the only if direction of the proof. If we have a solution to independent set, we can get a solution to the SAT problem. So this is the only if direction, I think. Yeah. So if we know there's an independent set of size m, where m is the number of clauses, then we can create a satisfying assignment for phi. So that gives us 1/2 of the proof. That's the idea. Now, to actually compute the graph, the reduction, we can build in polytime. And if you just do it the dumbest way possible, it'll take O of n squared time, because for each variable, you might have to search through every literal or every clause to find all the edges. So for each node, we might do linear time to create all the edges for that node. And so over all the nodes, it'll be n squared. You can probably do it faster, but we just care about it being polytime. So n squared is good enough. Yes?
Fully understanding how this is solved. So we start out with a set
Formula, yep.
and then we turn it into a 3-set formula.
Well, we're starting with the 3-set formula.
So
Yeah,
we
you
start-
don't have to worry about that conversion.
Okay, so we start with a 3-set formula.
Mm-hmm.
So we just have a formula like that given to us.
Yep, you're given this formula.
Okay.
And then you're just converting it into this graph.
Okay. And then you use the maximum set to figure out the maximum.
Yeah, so specifically I'm using the decision version. So I'm just asking, is there an independent set of size m?
Okay, so let's say it's like 3.
Mm-hmm.
And then we figured out there is a maximum independent set of 3. What do we do there?
We say true.
Oh, that's it.
Yep. So this will have an independent set of size m exactly when it's satisfiable. So our algorithm is just going to run the independent set black box algorithm and just output the same output. If it says true, we say true. If it says false, we say false.
So I was confused because like you're doing like 1, 1, 1, 1 for the like A, like not B, C, A part.
Mm-hmm.
So that was just to like show us that it's actually not touching. Right?
This is just to explain like the idea behind the construction. The reason why this construction works is because it's corresponding to a specific assignment of phi. So we're literally ensuring that a solution to one of the problems gives us a solution to the other.
Okay, so we actually do have to find a balanced solution.
Yeah, we do. So if the independent set in G does not have size m, if it's smaller, then that means we could not satisfy phi. We couldn't find a setting of the variables that made all the clauses true.
So the question was, let's say that we do figure out like there is a independent set of size 3.
Mm-hmm.
We have to actually figure out what that set is, or
No,
we don't have to.
this is just the decision version.
I
Yes.
was wondering if we had to find out like the A, C, D, right?
Yeah, you don't have to, but in the proof we're going to do that.
Okay.
I think that was my question. I was going to ask, how do you figure out what is an independent set? How do you get the connectivity of like A, B, C, not B, A, not D, like so on and so forth?
Like how it's actually computed?
Yeah, like how is the connectivity?
Magic.
Okay, so it's just we're black boxing that.
Yep.
So we have some black box function and it spit out 4 4 different independent sets.
No, just say yes, there exists an independent set of size 4.
A size 4.
Yeah. Because the important thing is the number of things in the set. Because if it was size 3, that means one of the clauses did not have an assignment, which means one of the clauses will be false. Well, that's what's going to be.
Where did 4 come from?
In this example, there's 4 clauses.
Well, like that's like a hard. Is that like a hard coded thing that we're saying, or just? I'm like,
In this example, it would have to be 4,
okay.
because each item in an independent set corresponds to making one of the clauses true. And we need to make every clause true.
Right, but I guess I'm wondering why do we have 4 clauses specifically? What's stopping us?
Oh, that's just the specific formula.
Okay, all right. So
Yeah.
that came from the black box. That we have 4.
No, this is just from the specific example. So I'm giving you this specific input formula, and this is the specific graph that we construct. But the formula in general could be 50 clauses, it doesn't matter. It's just a specific example to illustrate what the reduction looks like. No, there's a. So these are 2 different nodes.
Oh,
Yeah.
they're
It's just the literal that corresponds to them is the same.
The red lines represent.
Those are these edges, the edges between the negations. So B bar connects to B.
wait, so those two A have different values?
No, so the nodes are different because they're corresponding to different clauses, but the variable inside could be the same. So when you set A to be 1, you're setting both of those A's to be 1. But remember, they're in different clauses. They appear in different places.
But isn't that still set of size 3? Like for the result?
No, because the node is not called A. The node is called Lij. It's just Lij corresponds to the variable A. So this is Lij and this is Li prime j, or maybe j prime, you know. We're identifying each literal by a unique identifier. So like you could have multiple literals that refer to the same variable, but they're distinct literals. They appear in different clauses. And so in the graph, the actual node representation is going to be distinct. So this won't be node U and node U. This will be node U and node V. We just understand that they're associated with the same variable.
So, yeah, but doesn't that like also result in there only being 3 numbers? Like 3 distinct numbers?
Yeah, so there's 3 numbers, but all 4 clauses are going to be 1. We need each clause to be equal to 1. Yeah. So each node being picked corresponds to making that clause 1. Yes.
Is it possible if we choose A in a subgraph, but we don't choose another A in another subgraph? If that independent set helps.
Yeah. That's totally possible.
But it's not just coincide with the original problem, right? If we choose A, an arbitrary literal to be true, then all of the A should be true. In this graph problem,
Yeah, and they will be because of this condition. These edges make sure that the assignment is consistent. So if we decide to make A equal to 1, that will be okay because we'll never have an edge between A and A bar. Or we'll never choose both A and A bar.
but is it guaranteed that we choose A in all of the?
Oh no, yeah, if A was not chosen, we can make it either value. It's just not relevant to making the whole thing true. Yeah. All we care about is making the literals true that make the clauses true. The other ones can be whatever. They don't affect us. The second even a single literal in a clause is true, the clause is true. We don't care if there's 2 ones or 3 ones, we just need a single one. So I think looking at the proof might help clarify a little bit. So, phi is satisfiable. Let's suppose phi is satisfiable. So we know there exists some x1 to xn, so that phi of x1 to xn is 1. And in the example, we used like a, b, c, and d, and whatever, but I'm just going to call them x1 through xn to make it more general. So let's suppose I had these x's. So what am I going to do? Well, for each clause, we're going to set, or we're going to pick the set, look at each clause. So let's fix a specific clause, say C. C is something like L1 or L2 or L3. And because phi is satisfied, we know at least one of those literals is true. So whichever is true, we're going to place LCI in the independent set. So remember, for each clause, we have 3 nodes in the triangle. And so I'm just saying in that triangle, I'm going to pick this specific one. So in the triangle corresponding to clause C, I'm picking specifically this node, LCI. This one specifically goes in the independent set. And that's the one that was true in the formula phi. Okay? So now we know there's a total of m clauses. That's just by definition. And so since we're picking one node per clause, this implies our set, which I'll call S. This implies our independent set has size m. So because we picked one node per clause, we have m nodes. But is it an independent set? So I think the easiest way to see it is from contradiction. Suppose there was an edge between some LCI and some other L, I'll call it DJ. So there's 2 ways this could happen, right? So either LCI is the same as LDJ, but the complement. So this is the case where you have like A and A bar. So if that was true, that means we must have set the variable. So let's say this one's the variable. It's some xk. So we set xk equal to 1, and we set xk equal to 0. That's the only way both of those could be set to 1. It's the only way both LCI and LDJ bar equal 1. Right? If both A and A bar are both 1, that means A is 0 and 1 at the same time. But clearly this contradicts that X is an assignment. Okay? So the other case, so that's one possibility. The other case is that they're in the same clause. So the other option is LCI and LDJ satisfy C equals D, so same clause. But this is an issue because by definition, we only pick one of these nodes per clause. For every single one, we picked exactly one of the nodes to be in the clause. But this contradicts the definition of S. One node per clause. So we know S is independent because X being a valid assignment makes sure those edges can't exist in the set. And because of our specific choice of S, the other edge can't be in the set. And then we know it's full size, it's size M, because every clause was satisfied. So overall, this implies S is an independent set of size M. So for the other direction, if I give you an independent set of size M, so let's say S is an independent set of size M in G, then what's our formula X going to be? We set, so for any LCJ chosen in S, we set xk to be equal to 1 if xk equals LCJ, else xk equals 0 if LCJ was the complement of xk, if it was the negative. So why is this a valid assignment to phi? Well, first of all, because we chose one literal in the clause. So we chose one literal per clause to be true. This implies that phi is satisfied. Now, the only issue here is, well, even though we chose one literal per clause, that doesn't mean that two nodes weren't in the same clause chosen, and so that could be less than M. So this also follows from the fact that only one node per clause in S. Else has the edge in the triangle. So because we put triangles for each clause, we can only pick one of those nodes to be in the independent set per clause. And so if we have M of them, we know each of the M is in a distinct clause. Okay, so we know that the formula is satisfied. So the last thing is just to check that it's a valid formula. And it's a valid formula because if A is set to 0, it can't also be set to 1 because of the edge between A and A bar. So because the set's independent, we can't choose both A and A bar, and so each variable is assigned at most one value. And everything else not assigned a value, we can just set to a default value. So make it 1. Won't matter. And so overall, this setting we construct x is valid, and phi of x equals 1. And hence phi is satisfied. So phi is satisfiable. We know it's satisfiable because we found a specific assignment that satisfies it. And that completes the proof. So the takeaway here is, if phi is satisfiable, we use the assignment to construct a valid independent set in G of size m. And if G had an independent set of size m, then we can turn it into a formula phi that is satisfiable. Or we turn it into a specific assignment that satisfies phi. And this proves the reduction is correct. And so, independent set is NP-hard. So the general pattern, I'll just go through really quickly, because all of these proofs are basically the same, is when we reduce a problem x to a problem y, we need to do three things. Find a poly-time algorithm that transforms an arbitrary instance of x into a special instance of y. So this would be turning the 3-sat formula phi into this special graph we made. Then we have to prove if x is a good instance, so if it's satisfiable, then the graph we constructed has an independent set. And if y is a good instance, so it has an independent set, then we knew that the formula was satisfiable. And usually to do that, we do it constructively. So we actually transform the proof, or the certificate, which for satisfiability is a specific assignment, we transform the assignment into an independent set, and we transform the independent set into an assignment. So really, you constructed three algorithms. One for the reduction, one for the if part of the proof, and one for the only if part. And in general, when you're doing this process, when you're creating a reduction, you want to keep the proof in mind as you're creating it. So you want to design it so you know the if direction and only if direction will work. And just think what could go wrong. So maybe I'm creating this graph, and I didn't add those edges between A and A bar. Well, I could think, okay, in the proof, eventually I'm going to need to make an assignment. And so if that edge isn't there, I can make one variable true and false at the same time. So you want to be thinking of how the proof will work while you're coming up with the algorithm. And this is kind of like what we did with induction. If you think about it from the perspective of the recursion fairy is helping you, then you're getting this induction proof for free, because the recursion fairy is the induction hypothesis. So you're both creating the algorithm and the proof of correctness simultaneously, and that helps to make sure your algorithm truly is correct. Okay, so I'll stop there.